In this video, we'll be exploring the Coronagraphs tool on Predictive Science's new MHDweb 2.0. This tutorial is part 8 of a 12-part series that is designed to guide users through this website's data visualization tools. If you have not done so already, it is recommended that you review part 1 of this series, which covers in greater detail this website's architecture, general visualization workflow, and the mass run database. So with that being said, to get started with coronagraph comparisons, navigate to the MHDweb landing page, that is predpsi.com/MHDweb2, and click on the Coronagraphs button right here. For this demonstration, I'm going to select a run that intersects with the Mauna Loa Solar Observatory data availability range. To do that, go to the bottom here, click the start time for that, and the end time. So we have a time range of roughly between the end of 2018 and the beginning of 2024. So actually I'm going to go ahead, sort by start time, and select something at the beginning of 2020. Let's see. The Coronagraphs tool is designed to facilitate direct comparisons between simulated coronagraphs using PSI's MHD models and real-world white light imagers. Both this tool and the EUV comparisons tool are actively being developed as we work to supply a wider range of available imaging instruments for comparison. So at this time, MHDweb 2.0's initial release, the only observatory provided is Mauna Loa's Solar Observatory, namely their Cosmo K-Core instrument. The comparison instrument source can be selected from the instrument dropdown in the observation widget. As we include more instruments in future iterations of MHDweb 2.0, they will populate this dropdown menu here. For a given white light imager, we fetch their publicly available data through the Helioviewer API. This wonderful resource allows us to query and download JPEG 2000 images derived from science quality FITS files. This JP2 data is used to generate Sunpy maps and perform the necessary transformations and normalization routines to compare the maps with our model results. I'll provide links to this incredible resource in the video description below. As with other comparison tools, for example, time series, spacecraft mapping, EUV imagers, data availability is the sort of principal constraint which dictates which mass runs are viable candidates for analysis. This is particularly true for the coronagraphs page. The MLSO K-Core data available through Helioviewer lies within a fairly narrow time window between December 2018 and December 2022. As well as a small selection of observations around the 2024 total solar eclipse. The current pause to MLSO's data availability is actually a result of Mauna Loa's volcanic eruption in 2022. So although the MLSO facility itself was undamaged, the access road to the facility was destroyed, although they're actively working to restore access to the observatory. So given these data availability constraints, that's why I selected current rotation 2226, which spans January of 2020. The field of view in a Coulter, as you would expect, are defined by the instrument's specifications, and while we provide a default grayscale color map, this can be adjusted by selecting the color palette button here. Just like the white light tool, you can radially filter by applying some vignette function here, scale logarithmically, or radially scale it by some power n, as well as adjusting color bar scaling using the view widget down here. These data transformations and also color bar scaling will be applied to both plots. So let's say I change the radial power. Now both of these will be scaled by 1 over r, or say r squared. You can see these are happening to both the simulated and the observed plot. However, if you'd like to apply a distinct set of transformations and scaling to the two plots, you can see over here in the observation widget there's a distinct view button. And when you toggle that on, These set of transformations and scalings will be applied to the observed plot, and the previous widgets will control the simulated plot. Now, as you can see, some extreme value made its way into the observed plot. It's negative 4.62 to the negative 6, effectively washing out the plot. But if I set it to the same as the simulated plot for the minimum value, and then left the maximum value to be the max value that's supplied here, we can supply different scalings to the two different images. Alternatively, the radial power for the simulated plot is r to the negative 2, but I could change that to, let's say, 1 over r or r squared. So while we've done our best to apply a consistent scaling to both plots as the default options to yield scientifically accurate and meaningful comparisons between simulated and observed data, there can still be disparities between the dynamic ranges of the two data sets. So keeping this in mind, the distinct view option can be particularly useful when it's necessary to fine-tune the color bar scaling to yield plots that are not over or undersaturated. So one last parameter that I want to bring up that you'll see in the observation widget is this checked quality. Now, part of the metadata that is supplied by the Helioviewer API is a flag that indicates whether or not the JP2 image that is being supplied has sufficiently good quality for scientific comparisons. By toggling this on, you'll only be supplied with images that meet that criteria. If the specific time of interest that you've selected in the simulation widget does not have a JP2 image that satisfies this quality flag, what we do on the back end is query within a range of 24 hours available images from the Helioviewer API and return the closest timestamp that has a quality image. In general, when you're supplying a time of interest, we'll return the image with a timestamp that is closest to the time of interest provided. So just bear that in mind when you're querying a mass run towards the extremes of its time range, because the closest time range might fall just before the simulation or just after the simulation, and you could possibly get a validation error that says that there's no data available for this time of interest. For example, if I query the very beginning of this run time range, you'll see that it says no results found within simulation run. That's because the closest image to this timestamp is actually just before the run range. However, if I just move this time of interest forward by, let's say, an hour, or perhaps 2, you'll see that it is found a satisfactory plot to display. And one last thing to keep in mind is that this tool is a fairly data-intensive visualization tool, and it also involves querying the Helioviewer API, downloading that image, making necessary transformations, etc. So this process can take a little bit longer. So this tool in general is perhaps a little bit more sluggish than tools like Plot1D or Plot2D, for example. Well, that concludes this overview of the Coronagraphs tool on Predictive Science's MHDweb 2.0. The next video in this series will go on to explore the EUV and X-ray tool. If you have any questions, comments, or concerns, please leave a comment below. And thanks for watching.